We're just going to wait for a couple more judges to come in and then we'll start. Hello, welcome everyone to the 2021 International Student Paper Contest, PhD Division. We are very happy to welcome you all here today, and I would like to thank you all for joining us. Firstly, I would like to tell you a bit more about the virtual platform we are using. All participants will be using Zoom to present a pre-recorded presentation based on their technical paper. Only judges and participants will be allowed in the Zoom meeting, and all viewers are encouraged to watch and support the candidates using the comments box. As this is a competitive session, we request viewers to not submit questions to the presenters. Only questions from the judges will be considered as part of the contest. While the videos are playing, we will be keeping all participants muted. Judges and the participant will only be unmuted during the Q&A sessions. If you do have any questions or concerns at any stage, rather than interrupting the contest, we would like to ask you to email us at spc@spe.org. For our agenda today, we have 11 speakers presenting. Each have been given up to 20 minutes to give their presentation, which will be shown as a pre-recorded video. Once this video has concluded, we have approximately 5 minutes of questions and answers. Once all presentations have been shown, the live stream will close and the judges will review and deliberate their scores. The results of the contest will be announced at this year's Student Awards ceremony during the ATCE, and all viewers are welcome to attend this. Here you can see our presenters for today. I would like to thank them all for their hard work and dedication to help us get everything ready for today. All of the participants you will watch today have already won their regional competitions, so we can all look forward to the best work our student members have to offer. As part of this contest, many of our participants have elected to have their full papers published on One Petrol, and they have joined SPE's ever-growing collection of technical knowledge. Please do make sure to visit these papers for more depth onto their presentations. We still continue to experience restrictions on travel and mass gatherings. All of our student paper contests this year have been run virtually. Using this approach of hosting this contest for SPE, we have seen new skills shown by students and greater participation than ever before. Now let's welcome our judges for today's contest. Please welcome Mirel Tawfiq. Mirel, would you like to introduce yourself?
Can you hear me?
Yes, we can. Yes.
Yeah, sorry, I'm joining from my phone. I wasn't able to connect on the computer.
No problem.
Yeah, good morning, everyone. I'm Mirel Tawfi. I'm currently a reservoir engineer with Chevron in the Chevron Technical Center, and I'm calling in from Houston, Texas today. My background is in petroleum engineering, so I got my bachelor's degree in petroleum engineering from the American University in Cairo, back home in Egypt. And I got my PhD in petroleum engineering from Penn State. I'm really looking forward to listening to all your presentations today, which I'm sure are going to be extremely enjoyable. And best of luck to all of you.
Thank you, Mirel. We are now pleased to welcome Yongzhang Liu. Would you like to introduce yourself?
Sure. Hello, everyone. My name is Yongzhang Liu. I actually just got my PhD in petroleum engineering from Texas A&M University, and now I'm working in the Lawrence Berkeley National Laboratory as a postdoc. So I'm really looking forward to your great presentations, and I'm very happy to participate in this great activity. Thank you.
Thank you, Yongzhang. We now welcome Rita Ezura Okofor.
Hello, everyone. I'm Rita Okorafor. and I'm currently a postdoc at Stanford University. I also recently graduated from Stanford University in energy resources engineering, where I had my PhD. And before then, I worked in the oil and gas industry for about 13 years as a reservoir engineer. I really look forward to the presentations today, and I know it's going to be very interesting. Thank you.
Thank you, Rita. And we now welcome North Jabri. Hi, North. Would you like to introduce yourself?
Hello, hi. Can you hear me?
Yes, we can.
Yes. How are you? This is Nawfal Jabri. I'm a petroleum engineer working for the Exploration Advanced Research Center in Saudi Aramco, and I'm looking forward for your presentations. All the best. Thank you.
Thank you, North. And finally, we have Anil Kumar. Anil, would you like to introduce yourself? Hi, Anil, can you hear us? Can you hear me?
Yeah. Can you hear me now?
Yes, we can hear you, Anil. Thank you.
Okay, all right. Thank you. So my name is Anil Kumar. I have a PhD in petroleum engineering from Stanford. And I was chairman of Petroleum and Mining Department at New Mexico Tech many years ago. And subsequently, I worked for Chevron Mobile as a senior engineering advisor and also as a senior VP for Reliance. And some of you might know me as a father of pressure derivative because I presented the first two papers in pressure derivative going back to 1976. And so if you have had to study in your graduate school, you know, too bad, you know, that's, I'm the culprit, you know, who got you involved. So it's a real pleasure. I was actually a contestant once when I was a student. And I'm really looking forward to your wonderful presentations, and I know you all will do a great job. So thank you very much, and look forward to hearing your presentations.
Thank you very much for that, Anil, and thank you all, and thank you everyone for your contribution to this event. So I would like to take some time to thank our long-standing sponsors of the Student Paper Contest, Chevron. Even during these difficult times, they have shown a commitment to future engineers by supporting SPE programs like the Petrobras Championship, our Student Jews Waiver program, and of course, the Student Paper Contest. I would also like to thank Dragon Oil, who have generously supported the whole of ATCE as this year's host organization. And we would also like to give thanks to our patron for ATCE this year, His Highness Sheikh Hamdan bin Mohammed bin Rashid Al Maktoum, the Crown Prince of Dubai. So for those watching at home, we would like to give you an overview of the competition. Each of our contestants are the winners of one of the 14 regional student paper contests, and they have all proven themselves already. This contest today aims to showcase their talent on a global stage and seeks to find the top paper for a $1,000 prize. All contestants have already provided copies of their full technical paper, which the judges have reviewed, and both this and the upcoming presentations will be marked based on the content, relevant and delivery. To further increase the stability of this approach, we have asked all participants to pre-record their presentation in advance. This video will be shown by the moderator to the judges for the first time during the session, and all judges will only watch this video once when submitting their score. Once the video has been played, the participant will be invited to have a live question and answer session. The Q&A will last approximately 5 minutes. Judges have also access to the presentation slides and full technical papers. Once all papers have been shown, the live stream will end and the judges will be allotted time to submit and reflect on their scores. The judges will rank the contestants, and it is the ranking that will combine with the other judges' rankings to determine the winner. Once all scores have been submitted, the judges will come together to verify the results. We will be announcing the results of the contest during ATCE Student Award Ceremony this Thursday. Now let's get started with this year's International Student Paper Contest for the PhD division. Our first presentation is Intisar Khalifa Al-Busaidi, who won the Middle East, North Africa and South Asia Regional Paper Contest.
Hello everybody, I am Intisar Al-Busaidi, PhD student from Sultan Qaboos University from Oman. In this contest, I'm representing Middle East, North Africa and South Asia. My presentation talking about an experimental investigation of the impact of polymer on electrokinetic properties of crude oil, brine, rock interfaces. We will start with a small introduction about the topic. Then we will talk about the current stats and objective, followed by the methodology that has been conducted, and after that we will discuss the main results, and finally we will conclude the main outcomes in the conclusions. Starting with the introduction. Several enhanced oil recovery technologies have been researched, developed and applied, which have led to significant improvement in oil recovery. Low salinity water flooding is one of these EOR technologies that revive the interest as cost-effective, environmentally friendly EOR, and several field trials and experimental works show success in improving oil recovery. However, the application of low salinity water flooding on field scale is still limited due to the lack of understanding the underlying mechanisms. Despite there is a general agreement that wettability alteration is the reason behind an extra oil recovery, and several mechanisms had been proposed for wettability alteration, such as fine migration, pH increase, multi-ion exchange, electrical double layer expansion. But what is the main mechanism that contributed to wettability alteration is still debatable due to the complex crude oil brine rock interactions. Polymer flooding, on the other hand, is a mature EOR technique which has been successfully applied worldwide to recover heavy or viscous oil. It also shows successful implementation in Oman at a large scale in Marmul field. The mechanism of polymer lies on improving water-oil viscosity ratio, resulting in better sweep efficiency and delays breakthrough of the water. The efficiency of polymer flooding mainly depends on the rheological properties of each bomb, which is controlled by salinity of makeup brine. Combining low salinity with polymer flooding in a technique known as low salinity polymer flooding shows a growing interest in petroleum industry, because it resulted in an increase in incremental oil recovery with a significant lower amount of polymer, therefore lower cost. Also, it shows an improvement in polymer stability, resulted in less scaling and soaring problems, shows better injectivity and lower absorption. However, ion exchange between polymer and the aqueous solution has been identified as a potential risk, because it can affect the viscosity of the polymer. Therefore, the efficiency of EOR technology depends on crude oil brine rock interactions. In the previous studies, crude oil brine rock interactions didn't receive enough attention in low salinity polymer flooding due to the complex interactions between low salinity polymer, rock surface, crude oil, and most of the experimental work discussed the technical and economical benefit of low salinity polymer flooding using core flooding experiment, as it was discussed in the previous slide. Moreover, no conclusive description of the active mechanisms behind high oil recovery from low salinity polymer injection. Also, the used oil in the published research so far has low viscosity. Therefore, this study aimed to investigate the impact of HBAM polymer on electrokinetic properties and crude oil brine rock interactions with different brine composition, salinity, and viscous oil. To conduct this study, crushed boy's outcrop with a mineral composition of quartz, feldspar, and clay minerals was used. For brine, deionized water was used as a reference point, as well as that calcium chloride, magnesium chloride, or a mixture of them once prepared in a concentration of 2 to 14 millimoles, which reflects the maximum and minimum concentration of divalent cations in Omani oil reservoirs. Also, synthetic formation brine and 10 diluted formation brine was prepared. Viscous crude oil with a viscosity of 160 centiboids and acid number of 0.68 milligram of potassium hydroxide per gram of oil was used, and HBAM polymer with a commercial name of Flowbam 3630S was utilized with a molecular weight of 20 million Daltons and 30% hydrolysis degree. For experimental procedure, Boyce powder was treated with brine alone and brine with the polymer. The samples were mixed and checked for 2 days at reservoir conditions. Then the solid was separated from the liquid by centrifuge, and the solid or powder after drying was analyzed by thermogravimetric analysis to check polymer absorption, and also its electrokinetic properties was analyzed by zeta potential measurement, while equilibrated brine was analyzed by pH measurement, zeta potential measurement with crude oil, and rheological measurement for polymer solutions. Moving to the most important section, results and discussion, starting with the zeta potential of Boyce-brine interface in absence of polymer represented by blue bars and presence of polymer represented by red bars. Zeta potential measurement show that Boyce in deionized water has negative zeta potential, which may be referred to the dissociation of selenium group in aqueous phase at a pH higher than 3, resulting in negative selenium group, making Boyce surface charge more negative. Addition of calcium to deionized water reduced zeta potential from -33 millivolt to -6.2, and further increase in calcium concentration resulted in a less negative zeta potential. In the presence of polymer in deionized water didn't affect the surface charge of Boyce. However, in case of calcium or divalent cation, presence of polymer make Boyce surface charge more negative, and this effect increase with increasing concentration of divalent cation or calcium in this case, which indicate that there is a polymer adsorption occur on Boyce surface. Two possible mechanisms can explain polymer adsorption on Boyce surface. The first one is shielding. Shielding will reduce electrostatic repulsion between negative charge at Boyce surface and negative charged polymer molecules. The second mechanism is that divalent cation may act as bridges between negative acrylate group on polymer chains and a negative surface charge, and hence increase polymer adsorption, making Boyce surface more negative. To check if this, or to make sure about the impact of divalent cation toward Boyce surface in absence and presence of polymer, we conducted the experiments with magnesium chloride solution, and the results reveal that calcium and magnesium have the same reactivity toward Boyce surface either in absence or presence of polymer. Next, we make the case more complicated. We compare the effect of a mixture of calcium and magnesium with equimolar of each divalent cation alone, either at low concentration represented by 2 millimole or high concentration represented by 14 millimole. The results show that divalent cation at a different composition, either in absence or presence of polymer, has the same impact toward Boyce surface charge. The difference lies in that impact of polymer increase with increasing divalent cation concentration, and this confirms that polymer adsorption increase with increased divalent cation concentration. Now let's go to real case to represent reservoir condition. Boyce surface charge was evaluated after contacting formation brine and 10 dilution formation brine. The result revealed that Boyce surface charge became more negative in the presence of 10 diluted formation brine compared with the formation brine, indicating that as salinity increased, Boyce surface charge became less negative, and the same trend was observed in the presence of polymer. However, more significant change was observed on Boyce surface charge after treated with polymer with formation brine, which indicate that more polymer adsorption occurred in presence of formation brine. Polymer adsorption was confirmed by thermogravimetric analysis to quantify polymer adsorption on Boyce surface charge or on Boyce surface. TGA curve of fresh Boyce and treated Boyce with 10 diluted formation brine, which are represented by black line and orange line, was almost similar, which indicate that low adsorption occurred in case of 10 diluted formation brine. However, TGA curve of treated Boyce with formation brine indicate sharp weight loss step at 480 Celsius, which is the temperature where polymer decomposed. So this is an indication there is a strong or more polymer adsorption in case of formation brine, as or this result is in line with zeta potential measurement. Then equilibrated brine and polymer solution properties was evaluated, starting with the pH measurement. The initial pH of brine was set to be 5.5. Addition of polymer to the brine resulted in an increase in the pH around 3 units. And why we have this increase? Just we have polymer with brine. That can be referred to the structure of the polymer, which is mainly consists of a copolymer of acrylamide and acrylic sodium. Acrylic sodium in water dissociated to produce acetate ions that react with water and producing abundance of OH ions that in turn increase the pH of polymer solution. Equilibrated brine with the Boyce also resulted in an increase in the pH around 2 units, and that can be referred to ion exchange and feldspar mineral dissolution reactions. However, in case of polymer, there is a slight decrease in the pH after contacting Boyce, and that can be due to the abundance of hydroxide ions, sodiums in polymer solution. So the equilibrium will shift toward left according to the Latchler principle, resulted in a decrease in OH ions and thus decrease in pH value. Equilibrated polymer solution with Boyce also was characterized by zeta potential and viscosity measurements. The result shows that there is a relationship between viscosity and zeta potential measurement of polymer solution. The higher the viscosity, the more negative zeta potential, and as divalent cation concentration increase, viscosity of polymer solution decrease and zeta potential became less negative. Why? Again, due to the shielding effect. Shielding reduces electrostatic repulsion between polymer chains, resulting in increased coiling between polymer chains and consequently decrease viscosity of polymer solution, and zeta potential between polymer chains became less negative. And the reverse is correct for or in absence of cations, where electrostatic repulsion between polymer chains increase, leading to expanding polymer chains and polymer, and hence viscosity of polymer solution increase and zeta potential became more negative. The same trend was observed in case of magnesium chloride solution or a mixture of both calcium and magnesium. Also, the impact of salinity, or in case of formation brine and diluted formation brine, shows the same trend as that of divalent cation, where high salinity resulted in lower viscosity of polymer solution and less negative zeta potential. The last part is zeta potential of crude oil brine interface in absence and presence of polymer. Zeta potential was evaluated to be the most negative in crude oil deionized water interface around -85, and presence of calcium reduced the negativity of the interface significantly. As calcium concentration increased, zeta potential of crude oil brine interface became less negative, up to 6 millimole of calcium chloride solution. Further increase in calcium concentration drives zeta potential toward more negative. And the same trend was observed in case of magnesium chloride solution. That might be due to the high intensity of divalent cation at crude oil brine interface, resulting in high adsorption of carboxylic acid group from crude oil, forming double or multi-layer of carboxylic acid group, making crude oil brine interface or the charge of crude oil brine interface more negative. Also, the impact of salinity on the charge of crude oil brine interface was evaluated, and as you can see here, as the salinity of the brine increased, the charge of crude oil brine interface became less negative, and the same trend was observed in case of polymer. One important observation here that the impact of polymer, as we see in case of divalent cation, increase with increasing divalent cation concentration. But in case here, for example, information brine, increasing the concentration or the salinity, the impact of polymer was low, and that could be due to the presence of other salts like sodium, sulfate, and other ions. After analysis crude oil brine rock interfaces, here is a summary about the impact of crude oil brine rock interactions on the efficiency of EOR technology. At reservoir conditions, zeta potential at crude oil brine interface was positive, and at brine rock was almost zero, with equilibrated brine of a pH around 7 and viscosity around 1 centipoise. Diluting formation brine to 10 factor or lowering the salinity to 10 factor resulted in higher increase in pH. Thus, it means that removal of, or this will enhance removal of adsorbed polar organic compound from the rock surface. More negative zeta potential at both interfaces, which means the thickness of electrical double layer will increase, make water film more stable, and this will affect the wettability, resulting in more oil recovery. If we make the salinity of brine the same, so we use formation brine, but we add polymer, what will happen? There is a slight increase in the pH, and more negative zeta potential at interfaces was recorded. Also, the viscosity of brine was increased, resulted in a higher oil recovery. But what will happen if we combine polymer with 10 diluted formation brine? Highest pH and more or the most zeta potential at interfaces was recorded. In addition, that viscosity of the polymer solution using the same amount as that of with formation brine was, the viscosity was very high compared with the same amount. So it means that the amount of polymer in low salinity brine is low, resulting in a higher oil recovery in addition to lower cost. In conclusions, the main outcomes are: presence of polymer affect electrokinetic properties of crude oil brine rock interfaces, and its impact is determined by brine composition. Presence of polymer in brine not just increase the viscosity but also generates high pH environment, reduce adsorption of polar compounds, and thus affect electrostatic interactions of crude oil brine rock interfaces. Similar reactivity of calcium and magnesium toward both surface charge as well as viscous oil in absence and presence of polymer was observed. Finally, 10 diluted formation brine attributed to lower polymer adsorption on the rock surface, more viscous and higher pH solution compared with formation brine. So from this study, it's so clear that understanding crude oil brine rock interactions is important in determining the optimal chemistry of injected brine as well as the amount of the polymer. Also, it determines that low salinity or low salinity polymer could be considered as a potential EOR techniques for this type of the reservoir. I would like to thank my thesis committee members, Prof. Rashid Al-Ma'mari, Dr. Dawood Al-Mahrouqi, Dr. Mafish Karimi, as well as my university and Petroleum Development Oman company. Thank you. That's all about my presentation. If you have any question, comments, or an idea, you are more than welcome.
Thank you. So we would like to now invite the judges to ask any questions.
Hello, this is Yongza. Can I go first?
Sure, go ahead.
Before I ask a question, I have a gentle comment is that during your presentation, please slow down your pace. And I suggest you summarize your key findings or the control parameters in your experiments in each slide, so we can better concentrate to your presentation. Otherwise, we kind of lost what you are talking about. This is my comments. And my question is that I'm wondering if there is an optimal salinity for the polymer flooding performance.
Yes, for sure. For example, from this study, we conclude with that as we reduce the divalent cation, the efficiency of polymer or how it affects the polymer viscosity, it can be, lowering the divalent cation concentration will make the polymer solution more viscous, so the efficiency of low salinity polymer will be high. This is according to the composition. According to the salinity, in decreasing the salinity, make polymer viscosity higher compared with the high salinity or compared with the formation of brine, and thus we increase the viscosity of the polymer in polymer solution. In addition to that, we reduce the amount of polymer used, and this is affect the capital cost.
Okay, thank you.
Very good presentation, Intisa. I have a question and a clarifying, just a clarification. So in terms of the question, throughout the presentation, you mentioned that you did the experiment at reservoir conditions. Please, what are the reservoir conditions when you say, talk about reservoir conditions? And the clarifying question is just, throughout the presentation, was the viscosity of oil 160 cp, or did you change the viscosity of the oil at any point in time? Thank you.
Thank you. According to the condition, the temperature was 46. For example, the aging temperature of samples, and the pH after treatment or before the treatment, it was 7. But just to make sure about the effect of polymer on zeta potential, we eliminate the effect of the pH. As you know, zeta potential is a function of pH, so we eliminate its effect by titrating with the HCl to make it constant at 5.5, because this was the middle range of sandstone reservoirs. And according to the oil viscosity, I use it as it is, without diluted or anything. So the viscosity was 160 centipoise.
Okay, all right, thank you.
Okay.
Any further questions from the judges?
Yeah, I can go next. Thank you for the presentation, Intisar. So my question is, you know that you had illite in your sample, and that's, you know, that clays generally play an important role in wettability of sandstone. So had you aged your sample in oil before doing your experiment, do you expect any changes in the trends that you see?
If we egged, did you mean if we egged the sample in oil before the treatment with low salinity polymer?
Right, yeah.
The trend may be different due to the capacity of the reaction that occurs, because the presence of oil can affect the capacity, the amount of the reaction, but not the reaction itself.
Thank you.
Any more questions from the judges?
Yes, I do have a couple of them.
Go ahead.
Yes. Intisar, a great presentation. I loved it. I have a couple of questions. First of all, did you try any kind of other type of rocks in addition to the pies. And for the aging, I heard my colleagues ask you about the temperature. Did you try at higher temperature? Like, for example, for most of the carbonate, you know, the temperature is above the 90 centigrade. The third question, and I'm sorry really for that, but the third question is, so you're adding like magnesium chloride as well as calcium chloride. Both, they can affect the kinetic of the hydrolysis of the polymer that have been used. So I'm wondering if you studied the hydrolysis rate and you studied the kinetics behind it and how the addition would affect the hydrolysis. That's all. Thank you so much.
Thank you. I will go question by question to not forget the question you asked me. For the first question, you asked about what?
Did you try any type of rocks?
Yes, I try. Boys, I use it just as a model for my because I work on the reservoir rock. So we use real reservoir rock, marmol and typhoid. And as you know, that it's very complicated to deal with the reservoir rock. So we use model rock to know it does this affect crude oil brine reaction. Yes, mineral composition play a major role in this reaction. What is the second question?
I even myself forget. Don't worry. The aging temperature. Did you try to do it at higher temperature than 45 centigrade?
No, just because
kind of low temperature.
Because this is the reservoir condition that we work on it. So marmol condition is 46. That's why we set the temperature at this range.
Perfect. And why you had it like in powder form? Your rocks, the rocks that you have used.
Because we use a static bulk test, because as I mentioned before, that most of the study on low salinity polymer flooding consider core flooding experiments, which is, okay, I have some observation on core flooding experiment. Why, if we need the reason at a different length scale, for example, I study it here in a bore level. So I need to crush the sample to know, is the core flooding experiment matching static bulk test or the trend will be different?
Okay. And the hydrolysis rate, how the divalent ions will influence the hydrolysis rate of the polymer?
Of course, it will affect the because it will increase the hydrolysis degree.
Okay. Perfect. Thanks a lot.
Okay. Can you all hear me? I have a couple of questions. Okay. Well, very good presentation, and thank you very much. So I have some. Let me ask you this. So when you talk about low salinity, what salinity are you really talking about, and what was your reservoir brine salinity?
The reservoir brine salinity already is low, around 5,000. And when I talk about low salinity polymer, we dilute it to 10 factor. Why? Because if we dilute, for example, the desalination of low salinity reservoir, it's not expensive. So we can work with low salinity polymer. I mean, we can dilute it to 10 factor.
And my second question to you is, so how are you going to implement this in the field? When you go to design your polymer flood, what are you going to tell people in the field how to design the polymer system for your particular reservoir brine?
Okay, good question. This will identify the key missing links that are need to explain observation at core flooding experiment. For example, at core flooding experiment and at a field scale, they say that low salinity polymer enhance oil recovery more compared with the polymer flooding alone and compared with the low salinity effect. Okay, what are the mechanism behind it? It's just combination of low salinity effect with the polymer flooding, or there is an impact of polymer on low salinity polymer flooding. And as we see from this study, that polymer play a major role in crude oil brine rock interaction. Second, we need to optimize the water, the injected water. So for example, when now we study the maximum and minimum concentration of divalent cation, we can range that at high concentration, we cannot use high concentration of divalent cation because we'll increase the adsorption of the polymer. Increasing adsorption of the polymer will reduce the viscosity and amount, the viscosity of the polymer, which in turn will reduce the capital cost. So like this, it's connected to each other. And the most important point that for example, at this condition, using boys with this mineral composition, using a brine with this composition or with this chemistry, this salinity and this composition of divalent cation, and this oil viscosity of 160 centibois indicated that low salinity or low salinity polymer could work as a potential EOR recovery, potential EOR for this type of the reservoir.
Okay. So one of the following question would be that early on you said that the recovery efficiency goes up because of change in wettability. Did you, in your experiments, you did not talk about it, but can you say something about, as this electrokinetic properties are changing, how is it impacting the wettability?
The impact of electrokinetic shielding or impact of polymer on electrokinetic properties, you mean?
Yeah, how the wettability between the crude oil rock brine interaction is happening.
Okay, here we compare low salinity effect and low salinity polymer. The presence of polymer and low salinity is not just increase the viscosity, as well known. Just we know that polymer increase the viscosity of the water, decrease the mobility ratio. This is the function of the polymer. What if we combine low salinity with the polymer? Polymer not just increase the viscosity, but also increase the pH. Increasing the pH will dissolve. We can remove, the adsorbed polar organic compound. This is one. The second thing that increase the electrostatic repulsion force, as you see that zeta potential between crude oil, brine, and brine rock surface became more negative. Becoming more negative, it means that the electrical double layer will expand. It means more film, water film between the two interfaces became more stable. And as water film became more stable, the wettability became, it changed from oil wet to mixed wet, or from mixed wet to water wet state.
Thank you. Thank you very much. Yeah.
Welcome.
Okay, so we have reached the end of our question Q&A session. So we will move on to the next presentation. Thank you, Mr. Safo, very much for your presentation. We now move on to Alexandra Sterbakova, winner of the Russia and Caspian paper contest.
Hello everyone, I am Alexandra Sherbakova from Skolkovo Institute of Science and Technology, and the topic of my research is selection of anionic surfactant adsorption inhibitors onto carbonate rock in high temperature and high salinity conditions. As we all know, more than 60% of the world's oil reserves are represented by carbonate reservoirs. Surfactant planning is one of commonly used chemical-enhanced oil recovery methods, but it's carried out mostly in sandstone reservoirs and not in carbonate ones because of high adsorption of anionic surfactants onto positively charged carbonate rock. Majority of anionic surfactants are not stable in reservoir water with high salinity and high hardness ions concentration, such as calcium and magnesium, and besides that, the temperature known for the projects is very low. So the problem is to find a surfactant composition for carbonate reservoirs with harsh conditions. The brine salinity is around 200 grams per liter. Divalent cations concentration is around 14 grams per liter, and the temperature is 70 degrees. The solution is a surfactant which was synthesized by BASF company especially for these conditions. It is stable in a narrow range of temperatures from 68 to 72 degrees, and that's all. And the aim of this research is the following. As the adsorption of surfactant onto carbonate rock is high, the aim is to supplement the surfactant composition with an adsorption inhibitor. Adsorption inhibitor is a sacrificial chemical which helps to prevent surfactant loss in the near wellbore area. We know two main groups of adsorption inhibitors with different mechanisms of action. The first group is alkalis. Alkalis are used as components of ISP and IS floods for many years. They create a negatively charged layer on the rock surface, and the recommended range of pH is from 9 to 12. In the result, anionic surfactants with negative charge repulse from the rock surface. Commonly used alkalis are sodium hydroxide and sodium carbonate, but they will precipitate in our harsh reservoir conditions, so we have to find some alternatives. The second group is represented by polyelectrolytes. Polyelectrolytes must possess the same charge with the surfactant, and if the surfactant is anionic, it means that the polyelectrolyte has a negative charge. Anionic polyelectrolytes adsorb onto the rock surface more likely than anionic surfactants, and this mechanism is competitive adsorption. In the result, a negatively charged layer also creates and surfactants repulse. Based on literature data, we selected a list of chemicals which can potentially be stable and active in our conditions and with our surfactant. The first group is represented by inorganic alkalis such as sodium hydroxide. We have to check that it will precipitate to be sure. Sodium metaborate tetrahydrate, sodium tetraborate decahydrate, ammonium hydroxide, and sodium silicate. We have one organic alkali, it's ethanolamine, and several polyelectrolytes such as sodium polystyrene sulfonate, sodium polyacrylate with molecular weight 3000, and another one, sodium polyacrylate. Its trademark and manufacturer are not specified because we haven't found any published data about this chemical. The first stage of our experiment was a compatibility and stability test at 70 degrees during 14 days. We prepared two groups of solutions. The first group was adsorption inhibitors dissolved in synthetic brine. The mineralization of our brine is 200 grams per liter. And the second group was a surfactant solution with concentration 1% dissolved in the synthetic brine, and we added adsorption inhibitors to this solution with different concentrations. So 3 components in one solution. And after heating for 2 weeks, we found out that sodium polyacrylate is stable in all range of concentrations which we selected, from 0.5 to 2.8%, and sodium metaborate tetrahydrate is stable in a narrow range of concentrations from 0.2 to 0.5 weight%, and these 2 chemicals will be used in the following experiments. Next, we performed pH measurements of our solutions. We used Mettler Toledo 7 compact duo unit to do this experiment, and the results are shown in the graph in the slide. The first graph shows the pH values for sodium metaborate tetrahydrate after 1, 7, and 14 days of heating, and we can say that the sodium metaborate is able to maintain the pH of the solutions at the level from 8 to 8.5. Yes, it's not enough to achieve the recommended range from 9 to 12, but still it's alkaline media, and the sodium metaborate should work. The second graph shows the pH values of sodium polyacrylate in a surfactant solution based on mineralized water, and we can see that it is not able to maintain the pH in alkaline range, but the mechanism of its action is another one. The next experiment was evaluation of influence of our adsorption inhibitors on interfacial tension on boundary with the oil. The results are shown in this graph. The dashed line represents the IFT value of 1% surfactant solution in mineralized water without any other components. And the blue circles show the IFT values of sodium metaborate tetrahydrate in the solution of surfactant in mineralized water, and red triangles show the IFT values of sodium polyacrylate added to surfactant in mineralized water. And we can make a conclusion that adsorption inhibitors have no significant influence on IFT. To perform this experiment, we used Cruise spinning drop tensiometer, which is used for liquid IFT measurements, and the temperature of the experiment was 70 degrees. Then we pass to experiments with rock samples. In majority of published papers, the authors use model clinical site bought from chemical companies, but we use real carbonate from oil reservoir. Here is shown methodology of carbonate rock treatment before using in the experiment. The first picture shows the core sample as is. It was a big stone of carbonate with weight about half of a kilogram with absorbed components of oil. Then it was crushed to particles from 1 to 4 millimeters and extracted with toluene in zinc start apparatus to clean the core sample. We selected the mild extraction with toluene not to destroy the original wettability of the rock surface and not to remove the absorbed oil components because it will dramatically affect the results of absorption test. At this stage, the core is ready for use in static absorption experiments, but to measure the potential, we need more fine particles with size less than 100 micrometers, so it was crushed using a vibration mill, and then the rock was ready for zeta potential measurements. Zeta potential measurements were performed with Malvern Zeta-Sizer nano-JS unit, and the method is based on electrophoresis. We used a U-shaped cuvette with 2 electrodes on one side and another. The results of the measurements are shown in the table in the slide, and we can see that the charge of rock in synthetic brine is positive, and the value is low. It means that the system is not stable. And when we measure the zeta potential of rock particles in surfactant solution in brine, the charge becomes negative, and the value increases. It indicates that the system becomes more stable. Thus, we prove that the surfactant absorbs onto the rock surface, and we need some chemicals which will be ready to decrease the absorption. Then we performed static absorption test. We took glass vials, placed 3 grams of crushed carbonate rock into the vial, then added 3 milliliters of the solution, sealed the vial, shaked, and placed into the oven preheated to 70 degrees, and then kept the vials in the oven for 24 hours to achieve the absorption-desorption equilibrium. Static absorption was determined using the data of IFT measurements before and after contact of crushed rock and surfactant solutions. 1% of surfactant is very high concentration, and of course it's in the range after critical micelle concentration, but we diluted all solutions by 4 and by 40 times, and then recalculated the concentrations after the IFT measurements. The results of absorption determination is shown in this graph, and we can say that the absorption of surfactant without any inhibitors is 9 milligrams per gram of rock, and it's very high. When we add 0.55 weight% of sodium metaborate, the absorption decreases up to 4 milligrams per gram of rock, and when we add 1% of sodium polyacrylate, it is 3 milligrams per gram of rock. We can conclude that our chemicals work and decrease the absorption of surfactant, but the values are still in the 1 order of magnitude, and the absorption is still quite high. Besides that, we noticed that surfactant washes a part of hydrocarbons which were not extracted by toluene. It can be seen from these pictures. We can see the picture of surfactants before contact with rock, they are clear, and after the contact with rock, they become yellowish. And it's clear that some hydrocarbons passed from rock surface into the solution. Presumably, surfactant washes some hydrocarbons and settles onto rock surface instead of them. To prove this idea, we conducted an additional experiment. It was a pyrolysis analysis, and it was performed by Hawk Resource Workstation, using Hawk Resource Workstation. And the temperature program for carbonates with temperature of oxidation was 850 degrees. Here is shown the pyrogram for two samples. The first sample was carbonate rock extracted with toluene, and the bold black line is the pyrogram of the sample in the graph. And the thin black line represents the carbonate extracted with toluene after surfactant treatment. We can see that the pattern of these two pyrograms is very similar, and we can say that surfactant molecules wash hydrocarbons before C35. It is S1 and S2. They remain after toluene cleaning, and molecules of surfactant adsorb on the rock surface. We made an additional pyrolysis test of surfactant solution, 1%, with module without any hydrocarbons, and the signal of the surfactant coincides with the signal of rock sample after surfactant cleaning. So it means that the surfactant settles on the surface of rock. So finally, here are the conclusions of our work. We selected a list of alternative adsorption inhibitors based on literature data and selected two stable chemicals, which are sodium metaborate tetrahydrate and sodium polyacrylate. They don't affect the interfacial tension on the boundary with oil significantly, and sodium metaborate is able to maintain the pH at the level from 8 to 8.5, and so sodium polyacrylate is not able to maintain the pH in alkaline range. Additions of sodium metaborate and sodium polyacrylate to surfactant composition decrease its absorption twice, and surfactant molecules wash hydrocarbons before C35, remain after toluene cleaning, and thus can improve oil recovery. The surfactant settles instead of them on rock surface. Besides that, further investigation of dynamic adsorption is planned to obtain more representative data. Finally, I want to thank the Zarabezhk company for funding this research, and if you have any questions, I will be very glad to answer. Thank you for your attention.
Thank you, Alexandra. So we would like to now invite any judges, our judges, to ask any questions.
So I have a couple of questions. First of all, a great presentation. Thank you so much. And a great job as well. So the first question is, would you kindly elaborate a little bit on your IFT results with shedding the light on the inhibition mechanism? Because as you stated that the inhibitor didn't affect the IFT, so I would really appreciate if you can elaborate on that. And the second question, as I understood, you used anionic surfactants. So did you try any other type of anionic surfactants rather than the one that you used? Or did you even expanded the searching criteria a little bit to include other type of surfactants? That's all. Thank you.
Thank you for your questions. The first question about IFT measurements. The goal of this experiment was to check whether our additives such as sodium metaborate and polyacrylate effects on IFT, maybe they increase it, maybe by an order of magnitude or so on, and in this case, we won't be able to use them. And the experiments showed that they don't affect so much, so it was suitable for us. The goal of adding these chemicals to the surfactant was not to improve the oil recovery, but decrease the absorption. And the second question about this surfactant, it's the main issue of all these projects. I want to say that this project started several years ago, and the company Zarubezhneft, they wanted to select a surfactant for their oil field with harsh conditions. It was mentioned that the salinity is more than 200 grams per liter and the temperature is 70 degrees. And they tried a lot of different surfactants. They didn't go, and all of them stratified, formed precipitations, and so on, were not stable under these conditions. And they made a collaboration with BASF company, and BASF company synthesized a special chemical blend, surfactant blend, for these conditions, which was stable. And our task was to select some additives to this composition, such as adsorption inhibitors, to prevent the surfactant loss in the near wellbore area. Besides anionic surfactants, they also tried cationic with mixture with non-ionic. I also tried these mixtures and checked the IFT, the stability, but it was decided that the use of cationic surfactants is less effective in our case, and it's expensive. So that's a short history of this topic.
So I have a question here. Thank you, Alexandra, for a very nice presentation. And so what is the final outcome? Are they going to use this surfactant for their oil field application?
Yes, we can use this surfactant for the oil field applications, and even the trial injection into the wellbore was performed, and it showed that it is suitable. And we also can use our additives, but we have to continue our adsorption research, because the method with IFT is not precise. We tried a lot of methods to determine the absorption, and finally we found the HPLC methodology. So very soon this work will be continued. But yes, we can apply this chemical blend.
Follow-up question. So was there any core work done in terms of recoveries with this surfactant to know what kind of additional recovery you might obtain?
I don't know which additional recovery was obtained, because this data is not published. So I think it's commercial data.
Okay, thank you.
Hey, Alexandra, questions for the judges?
Yeah. So thank you, Alexandra, so much for the nice presentation. I have two questions. So first, the sodium metaborate, from your stability result, it shows that it precipitates at 14 days. So in a real world application, that would be problematic, since 14 days is such a short period of time. So my question is, have you tried any tests to see if such precipitation can cause maybe pore plugging or permeability reduction over time in that particular field of interest?
We haven't done this yet, but it precipitates not in all range of concentrations. If we decrease concentration from 0.1 to 0.3%, the precipitation was not occurred even after 30 days of thermostability test.
Okay. And my second question is, can you elaborate more on the crush drop before and after toluene cleaning in slide 10? I didn't quite get what you were trying to demonstrate there.
I'm sorry, maybe I didn't get the point of the question about the toluene cleaning.
Yeah, you had two images of the rocks before and after. I just want to know what you were trying to show in this one. I missed it.
Yes, I wanted to show that the rock surface after toluene cleaning is not the same as after surfactant treatment. So the surfactant eliminates some hydrocarbons which were absorbed maybe it was not the best interpretation, but we proved that it's a fact that it washes some hydrocarbons. So if we magnificate these pictures, it will be different.
Thank you.
Any more questions from the judges? Okay, so I'll take that silence as a no further questions. We're just going to take a quick short break because I just need to redo the stream, live stream. So we're just going to have a quick pause for about two minutes and I'll be back. Thank you.
Give us 5 minutes, can you?
Yes, of course. If you need to take a short 5-minute break.
Yeah, let's take a bio break. Thank you.
No problem. Thank you so much. We'll be back. We resume back at 12, was it 1:15? No, yeah, 2:15.
Okay.
So 15 minutes past. Thank you.
All right. Thank you.
Okay, brilliant. Thank you so much.